Okay, I guess I'll start.
Yeah. So can you just
Do you have a question?
hand in the extra credit for lab 2?
Hand in the extra credit for lab.
The actual lab.
What do you mean, instead of the actual
or,
lab?
Or
no.
is it a prerequisite to have the lab to get the extra
Yes,
credit?
that's true. And from now on,
Okay.
you first have to hand in your lab as it is specified, and then the extra credit.
Okay.
And extra credit is substantial for lab 2.
Yes.
If you have started looking at it, you'll see it. Okay, this is lecture 5. We're going to cover probably mostly single-cycle architectures, but I'd like to go through them very quickly because the concept is really simple. But you're going to be designing it for lab 2. I guess before we get started, lab 1 is due today. How many of you are done with it? Cool, that's a good number actually. How many of you are struggling with it? So. Okay. You think you'll be done? No? Well, try to get done as early as possible. We have some late days. You have a total of 5 extra late days that you can use it for any lab. But don't use it for the first lab. I wouldn't recommend it. Lab 2 is out. I would suggest starting as early as possible. This is going to be fun. This is going to be basically what I'll be describing today for MIPS. You're going to be doing it for ARM. It's a single-cycle ARM microarchitecture that you're going to be designing. And the extra credit is making it micro-programmed, which is actually exciting. Maybe in a future incarnation of this course, we're going to make a lab fully micro-programmed. And the extra credit is substantial. It's going to be about 4% of your entire grade for the course. I know you're not here for grades, but it's good to get 4% for no reason, right? Well, it's not for no reason. It's because of the hard work you put into the extra credit. Right? So I would suggest starting out early. And you'll have enough time. Well, you'll have more time for this lab since it's going to take longer. It's going to be an exercise in Verilog, for sure. Homework 1 is due next week. And there are some homework 0 issues, so I decided to extend the deadline. I don't know if this is a human error or if these are human errors or if these are tool errors, because some of the PDFs that were turned in, actually quite a few of them, were not filled in, even though they may have looked filled in to some of you in some editor. And I can understand that because I've run into that issue before. So I'd like you to check all of your forms and make sure they're correctly filled in and readable. I've sent email to some of you. I think Rachel sent email to everybody whom you found had problematic submissions.
Well, if you got an email from me, make sure you check with a different PDF reader, like maybe 2 or 3 PDF reader, and make sure all of them can read the PDF that you have.
That's right. Yes.
If we didn't get an email, can we assume that it's fun?
If you didn't get email, I open your submission and I can read them, the pictures somewhere, and they are fine.
Okay. Yeah. If Rachel can read them, that's fine. I didn't go through all of the submissions because I started hitting these submissions that were actually problematic, that had nothing in them. Even though you guys thought that you filled out something. Okay, so there's an extended deadline to resubmit. By Sunday night, please submit these because I do actually read them and I try to comment on them. This is how I get to know you more quickly, if you will. Hopefully I'll get to know you a lot more during this course of the semester. Okay, any questions on any of this? Everything is going well? You're learning a lot from the labs, homeworks, lectures? Okay. Yeah, if you have any feedback, feel free to let me know and let the TAs know as well. You can send email to any of us. Any feedback is appreciated so that we can adjust the course. This is going to be a tough course, there's no question about that. Don't tell me that it's really tough because I know that. But tell me you're going too slowly, you're going too fast. And there will be contradicting feedback from different people because not all of you have the same style of learning. So we'll try to adapt as much as possible. Okay, so definitely seek help if you're falling behind. Okay, we had started single-cycle microarchitecture in the last lecture, so we're going to delve into it a little bit. I'll do a closer look into what you're going to be implementing in your lab, lab 2. But I'll go through this relatively quickly because a lot of the concepts are really simple once you start looking at it. And then I'll try to get to multi-cycle microarchitectures today. Okay, good plan? If you think we're going too fast, stop me. But remember, this was a single-cycle machine, right? It consisted of some state and some next state logic, which is purely combinational. And every instruction got executed in this combinational logic. And you could do a single instruction in a single long clock cycle, right? So let's try to build this combinational logic, well as the sequential logic, probably. And let's try to look at a single cycle machine that implements part of the MIPS ISA. I'm going to use MIPS because that's what we've used previously, but you're going to do ARM implementation, but it's going to be very similar conceptually. The bits, where they come from, they will be different, obviously. The instruction semantics could be a little bit different. But the concepts, which are the most important parts that you should really get out of this course, at least the lecture part of this course, will be the same. So let's start with some state elements first. What is the sequential logic that we're going to consider? Certainly the program counter is part of the architectural state. Register file, we're going to have a register file that has 2 inputs and 1 output port. Well, that doesn't make sense, right? 2 input ports and to get the register IDs, and 2 register read ports, output ports, and a write port, and a register write signal. So this is basically a control signal that we're going to assert based on the instruction we're executing. And memory is part of the architectural state also. We're going to assume instruction memory versus data memory. We're going to separate them first. And we're not going to deal with a complicated hierarchy in the first lab. We're going to assume it's like magic, almost. You can get the data in one cycle. In a future lab, you'll see that you'll build this memory hierarchy at the C level. It's going to be fun. So instruction memory, basically, you supply the instruction address and get the instruction. And this is the data memory. You supply the address, get the data, or you supply the address and write data and assert the mem write signal to write the data. And there's also a mem read signal. If you want to do a load, you actually enable the memory in this case. Okay? So we're going to start with these basic state elements, and we're going to assume magic memory and register file. What do I mean by that? Basically, we're going to have combinational reads. Output of the read data port is a combinational function of the register file contents and the corresponding read select port, so that we can get the architecture. And this is what's needed to implement a single cycle microarchitecture. And we're going to assume synchronous writes. Basically, write the write register ID, provide the write data, and the selector register will be updated on the positive edge of the clock transition when the write enable is asserted. Which means that this write is not going to affect read output in between clock edges. Okay? Which means that you have the full read value for the full clock cycle, and you can do whatever you want with it. That's also needed for a single cycle microarchitecture. Right? Your write should not interfere with what you have read. Right? Okay? Well, memory will be single cycle synchronous. We're going to change that later on. Again, this is a very simple machine, and this also points to the downsides of a single cycle microarchitecture, right? But contrast this with memory that tells when the data is ready. You can have a memory that takes multiple cycles, but asserts a signal saying that it's ready. The data is ready. And we'll see this later on. Memory can have a ready bit indicating the read or write is done, but we're not going to have this for now. Assume single cycle synchronous memory. So let's remember the instruction processing. We had 6 generic steps, but Patterson and Hennessy, in their book, which I'm going to follow for part of this lecture, have 5 generic steps. Instruction fetch, instruction decode, and register operand fetch. Actually, let me do this over here. This is how we connect the state elements at a high level. You fetch the instruction with the program counter, supplying it to the instruction memory, and you get the instruction at the end. After that, you go into the decode and register operand fetch stage. Remember, it's happening in a single cycle. This is the instruction decode and register file read stage. Control signals are generated as well as registers are read if needed. And then there's an execute evaluate memory address stage, which happens over here. If you have a load or store, address is generated. If you have an ALU operation, the ALU operation is done over here, if you have an add, for example. And then there's a memory operand fetch stage or step that's done for stores and loads. And then store write back result stage. That could be done for register operations that write into a register, as well as load operations that also write into a register. Right? These are 5 generic steps. And you're going to basically design something that looks like this. Well, more realistically, you're going to design something that looks like this. This is the MIPS single-cycle data path plus the control logic, although control logic is not shown here. How you generate those signals is not shown here. But the data path signals are actually shown. What are the control signals that are controlling different elements? Let's try to build this. So how do you go about doing your lab 1, basically? This part of this lecture will be about that. How do you build this? Well, you start with instructions, right? Remember, we're processing instructions. And we're going to start with this basic thing and add functionalities for different instructions to it. Well, first let's take a look at arithmetic and logical instructions. Remember, this is MIPS. MIPS is nice. Your life will not be as nice, unfortunately, with ARM. But remember, it could have been worse.
Six.
It could have been worse than that also with VAX, right? That would be a blast from the past. But you would be some of the unique people in the world who know VAX architecture really well. Not sure if it's if it would be very valuable though. But ARM would be valuable. x86 would be valuable too. MIPS is a good instruction tool, I think. So. And remember, the underlying microarchitecture will be very similar. So this is the add instruction in MIPS. This is the R-type ALU. Remember, MIPS had R-type, I-type, and J-type instructions. Basically, you have 3 register operands, well, 2 source operands and 1 destination operand. And opcode is always 0. And you have the function over here with the add. In this case, it's an add. Basically, you're going to decode this instruction somehow. And if, this is the semantics of the instruction, if the memory location at this program counter contains an instruction that looks like this, add, R-type add, then this is semantics. You need to source RS, you need to source RT, get the data values, add them up, write to the destination register, and also increment the program counter. Simple, right? Now you implement the semantics. How do you do that? Well, it's simple actually. Basically, this is the data path for this kind of instruction. Once you decode it, you need to generate the right control signals. Remember, instruction processing viewed another way. There was one slide in the last lecture. Consists of data path processing as well as control processing. You need to design both the data path as well as the control signals that are necessary to process that instruction. In this case, the data path is simple. You need to fetch the instruction, you need to read the register, you need to do the ALU operation. In this case, it's an add, and you need to be able to increment the program counter. Now, you need to also set the control signals, right? Control signals, well, they're input signals to the registers. These are register IDs, and they're coming directly from the instruction. It's 25 through 21 for, I guess, register S, bits 20 through 16 for register T, and for the write register, destination register, bits 15 through 11. Okay. And register write signal should be asserted, right? Because this instruction is writing to a register at the end of the clock cycle. So you need to set that register's write signal to 1, and the ALU operation needs to indicate an add. Make sense? Okay, it's pretty simple for this. Now, let's take a look at I-type ALU instructions. This is the immediate type. Basically, you have a different opcode here, and this doesn't have an RD. Instead, RT is used as a destination. Basically, the semantics is that get the register specified by RS, add to it the sign extended immediate, and write the result to a register specified by RT, and also increment the PC, assuming if the memory location at program counter is this type of instruction. Make sense? So you can actually generate the control signals by checking this, but we'll take a look at the control logic soon. So what does the data path for this look like? Well, it's a little bit different now, right? We're gonna expand the data path by adding more instructions. To be able to implement this instruction, you need to be able to take the immediate value from the instruction, basically bottom 16 bits, sign extend it, and feed it to the ALU. But ALU also has another input, right, from the R-type instructions coming from the register output port, the second output port of the register. So you need to somehow be able to select between them, right, to be able to execute both instructions on the same data path. So and also, there's this idiosyncrasy. The destination register for this is RT, which is specified by bits 20 through 16. whereas the destination register for a R-type instruction is RD, which is the next 5 bits, specified by next 5 bits, 15 through 11. So you need to select between those two depending on the instruction type, right? Basically, if the instruction is I-type, immediate type, then you select RT as the destination. If it's also immediate type, this MUX is configured to select this output of the sign extension logic instead of the register output port. Make sense? So for the immediate instruction, this I-type is set. And register write signal still stays at 1, and ALU operation still stays at add. Now we're building the data path. We're going to add on top of this load and store instructions. Is this clear to everyone? Okay, have you done this before? Yes. So, sort of? Not for MIPS, maybe. Okay, so I'll go even faster. Okay, load instructions. Load instructions are also I-type, actually. Its opcode is different, but you have a base register. It's really RS, source register. RT is the destination, and you have an offset instead of immediate. And the semantics is, basically, if you decode this thing, you first calculate register, and adding to it the sign extended offset, very similar to what we've seen with the I-type instructions. So the control will be very similar, and we don't need to add to the data path. But also you need to access memory. There's some translation logic because MIPS has virtual memory, but we're going to ignore that for now. We're going to take just the effective address and feed it to memory and get the data, write it to the register specified by RT bits, and also increment the program counter. Well, I guess I forgot to increment the program counter. You need to have logic that increments the program counter as well, right? Make sense? I forgot it for the previous instructions, but you need to have that. That's what this logic does. So for the load, to be able to add the load to what we had before, oh, that's it, basically. Although it's not fully connected over here. I guess I should have connected it. Basically, you do exactly the same thing you do with an add that's I-type, right? Because add that's I-type, basically, you can think of this as base plus offset calculation, right? Sign extend offset. You do exactly the same thing, which gives you the address of the instruction, address of the memory location that the load is going to address, and you connect it to memory's address. It's not done here, but you can imagine that there's a connection. And also you assert the memory read signal for this load instruction. And that enables the operation of the load on the same data path with the memory added now. And is I-type is set such that you select the right registers as well as the right immediate. Okay? And you, of course, write to the register file because you have a register file right in this load. Okay, simple. Okay, what about stores? Stores are also I-type. Basically, address calculation is very similar, base plus offset, except stores write to memory. They do not read from memory. So the only difference over here is, well, I'm going too fast. Obviously, stores don't write to the registers. So register write signal is set to 0. And you still supply the ALU result to the address input of memory. Instead of asserting memory read, you assert memory write in this case. So control signals are selected such that it's ensures that the store operation is satisfied. Okay? So these all can operate in the same data path. If you put loads and stores together, they need to be able to operate in the same data path. This is how when I connect these things. Now the ALU result gets connected to the address input of memory. This is base plus offset. And now we add two different signals. Is store, is load. And you can easily generate these signals, right, by looking at the opcode. If the opcode is stored, is store is asserted. If is store is asserted, the write input, memory write control signal is also asserted because this store is directly connected to this control input. And register write signal is asserted if the instruction is not a store, right? If is store is false. Remember, we don't want this is load because there are other instructions that write to register, right? Operate instructions, for example, write to registers. But if you're doing a store, you're definitely not writing to a register. We're going to expand this later on, right? Obviously, some branches are not going to write to registers. So this control logic that controls this will be expanded. Okay? Does that make sense? And isLoad is connected to the memory read port. So now we're adding control signals also. You're going to do something very similar to ARM. In fact, you can use most of this for ARM with some small changes. Yes?
Why do you need an isLoad and isStorage? Can you just use one?
Actually, you don't really need them because you can name it anything. It's just the way I wanted to name it over here.
Okay.
You can name it anything, but I'm going to use this name later on in the control logic. In your design, you could keep it as memwrite, if you will.
Okay.
Okay. But basically, you need to have a signal coming from the control logic that controls that memory write output. And this is one way of doing it. Okay. Let's take a look at control flow instructions. Oh, wait a second. Okay, this is the load store data path. Now, okay, I knew there was a slide missing. This is the load store data path. Now we're going to ensure that this works well with the R-type and I-type operate instructions. So the only thing that's needed on top of this is basically this mux here. Why? Because if you have a load, you basically read the data from the memory and write it into the destination register. But if you have an R-type and I-type ALU instruction, you basically take the result, output of the ALU, and write it into the destination register. So you have two paths going into the destination register. Write data. Well, you need to select one of them, right, depending on the type of the instruction. That's why we have this mux. The input of the destination register data can come from either the output of the ALU or output of memory, and we need to select it. And that selection logic is controlled by this isLoad signal. If it's a load, then we select the input coming from the output of the memory. Otherwise, we select the inputs coming from the output of ALU. Make sense? That's how you build the data path with minimal additions. You could do it with more and more. Yes?
Is this the level of detail that you expect in the schematic for Lab 2? Like with muxes and stuff?
That's right, exactly, yes. We'd like to see your full design. Because this is essentially your control signals. It won't be that complicated. Of course, make it nicer than what I did over here. You guys are much better at drawing. What drawing tools do you use, by the way?
Visio.
Visio. That's it? Everybody uses Visio?
Pencils.
Which one?
Pencils.
I don't know that one. Pencils. Oh, pencils! Oh, this cold is getting at me. Is that Microsoft pencils? Yeah, pencils are fine too, by the way. You can draw it with your hand.
What did you use for this?
So I actually got it from the book. But I normally, when I draw figures, I use Xfig. Have you guys ever used that? It's a very simple tool. It's very basic, and I enjoy it because I can control everything on that one. Visio drives me crazy sometimes. This is an open source tool, but you can get anywhere. Okay. Okay, let's take a look at control flow now. We're going to integrate that too. But MIPS has several control flow instructions. You're going to implement several in ARM. One of the simplest one is unconditional jump. And the semantics is simple. Basically, opcode can be J, and the rest of the instruction specifies a 26-bit immediate that's concatenated with the top 4 bits of the program counter to form the target address. So you need to have this concatenation logic in your data path, obviously, if you want to do this. And then the target is placed into the PC at the end of the instruction execution. So this is very easy to add. We're not going to mess with this register path because we're not going to read any registers, right? We're just reading the program counter. And let's see. Yeah. Basically, before, we were just incrementing the PC. Now, PC can come from PC plus 4 if the instruction is not a jump, not a branch. But if the instruction is a jump, the PC really should come from PC, top 4 bits, concatenated with instructions, bottom 26 bits, and then left shifted by 2. That's the specification, because instructions are 4 byte aligned, right? They're 32-bit instructions. And this is jump signal controls where the PC comes from. If it's a jump, you select this input of the mux. Okay? Simple. Should I go faster? Is this boring? No?
Good pace.
Say it again?
A good pace.
Good pace. Okay. Okay. So you'll have to think about other things also. MIPS actually has, I don't remember which instructions. We have instructions with jump and link, right? That we specified for R?
Mhm.
Yes. Okay, that's good. We wanted to keep it very similar to MIPS. So MIPS have jump register, for example. It's basically jump immediate, but you save the program counter into a register. This enables procedure calls, right? Yes.
Just going off the question of, are you going too fast? Like, are we expected to know this level of detail for MIPS, like on a test or something, or?
Oh no, not for MIPS. I'm not going to ask
Okay.
you.
Like, I'm just
Where is this thing coming from?
I'm
MIPS?
just curious how familiar you expect us to do, like with the architectures we don't do in labs or something like that.
No, I would like you to know ARM
Okay.
well.
Well, yeah.
But the fundamental principles, the concepts, you should be able to know.
Okay.
For example, if I give you a data path that looks like this with some description of it, of course, and if I tell you an instruction and this is what it does, you should be able to tell me the control signals that you should set. Okay? But I'm not going to ask you which bits specify RS in MIPS. Right? That's not going to happen. That's memorization. That's not interesting. Well, actually, let me think. No, jump register is actually basically based on a register. I actually told you jump and link instead of jump register. Forget about what I said. Jump register is basically, instead of forming the target from the instructions bottom 26 bits concatenating with the PC, you basically have a register operand. You read the register, and that is your target. Right? So now the target can come from the register file. So you need to change this PC source mux. Now you have 3 inputs to the mux. And also, if you have jump and link, you need to save the PC to a destination register. And I'm not going to show you over here, but you can imagine the paths that you need to go through. Now your write data can come from multiple places, right? The PC can go into a write data port. Your mux is becoming bigger. There was a mux over here, if you remember. Okay. And this can get more and more complicated. It's fun. These are jumps. These are unconditional jumps. Conditional branches pose an even bigger problem, because unconditional jump, you know that you're going to jump. Right? Conditional branch basically depends on a condition, right? In this case, this is branch equal, for example. Branch if equal, you have 2 register inputs and an immediate input specified by the instruction. If the instruction looks like this, then the target address is calculated this way: program counter plus 4 plus sign extended immediate, sign extended left shifted immediate, let's say. And if these 2 registers, source registers, are equal, then target is placed into the PC. Otherwise, you basically go to the next sequential instruction. That's a branch, right? Branch if the 2 registers are equal. So you need to be able to support this. To be able to support this, well, this is one of the more complicated ones. Now you need to do a calculation to figure out whether the PC is changed or not. Right? To be able to do that calculation, well, let's see. Okay, there you go. You take the instruction and you sign extend it and left shift it by 2, the bottom 16 bits. Right? This is how you calculate the target. And you get the PC plus 4 from the instruction data path. And this is the potential target of a conditional branch instruction. It says branch target. It should be branch target, really. And that is an input to this PC mux that we had before. I'm going to simplify it. I don't have all the inputs over here. So that's how you calculate the target. But you also, I say watch out here, because you need to connect the right input to that adder, right? If you already incremented the PC, if you increment it again, that may not be good. Well, you somehow need to find the PC plus 4. You don't want to take the PC. You need to obey the semantics of the ISA, basically. Let me put it that way. Now, MIPS makes it more complicated because it has a delayed branch, which we will talk about later. It's a big mess. You don't have that in ARM. That's the nice part. Okay. Let's see. Well, of course, now you need to do the. This is the other part. This is the data path. This is the calculation of the branch condition, if you will. You read both registers, set the ALU operation to subtract, and there needs to be some branch control logic that I don't show here that checks whether the result is 0. Right? If you have a branch equal and the result is 0, then the branch is taken. And if the branch is taken, you better select the PC input coming from this add. Make sense? I'll let you figure it out. But it's pretty simple actually. If you haven't got it, you'll definitely learn it by doing it. And that's the purpose of the lab. And PC marks becomes more and more complicated, and we'll get to it later on. It has a lot of inputs. You can see over here, right? This lengthens your critical path, right? We're adding more and more to this mux because PC can come from the taken branch, PC can come from PC plus 4, PC can come from a register, PC can come from the jump target over here. I guess I'm not going to deal with this right now, but MIPS has an architectural semantic for a branch that's different from many ISAs. Actually, Spark has this too. The semantics is this way. I'll just give you the semantics. I'll let you think about why that is, and we're going to get to it when we talk about conditional branch, conditional execution, handling control flow instructions. The semantics is that you have a branch instruction, and then you have another instruction that comes right after it. Let's say this is at PC, this is at PC plus 4, PC plus 8, and some other instruction. The semantics is that the instruction that comes right after the branch is always executed, regardless of where the branch goes. Whether the branch is taken or not taken, this is always executed. So next sequential instruction is always executed. That's the semantics. This is called the delayed branch. At the ISA level, you have a delayed branch. It's delayed by one instruction, if you will. It takes effect only after this instruction is really executed. And this is called the delay slot. I'm not going to give you the reason why this was incorporated into the ISA, but I'll let you think about it. And if you really want to learn it, you can go back to the lecture from spring 2013 and satisfy your appetite. But we'll definitely cover it. But you can imagine that that's going to be, you need more modifications to this to actually uphold that semantics, right? Because you need to ensure that that instruction is really executed, and only after that you branch to the target. This just won't work. Okay? And that complicates the life of the architect. Although this was introduced to improve performance. Okay, I hope I've teased you enough so that you can take a look at why that exists. Okay, putting it all together, basically we've actually constructed, believe it or not, this thing. Well, maybe not all of it, because we haven't talked about control. But this is the data path. This is the data path that you're going to have, a little bit more complicated version of it. Okay? Makes sense? This is nicer because it has these muxes in a nicer way. Yes?
Should we also include the control in our data path?
Yes, definitely. Well, you'll need to generate the control logic, which is the topic of the next part. Basically, yeah, data path cannot operate without control, so you'll need to generate the control logic. Single-cycle control logic is actually easy, if you will. Basically, this is one way of doing it, and this is perhaps the only way of doing it if you have single-cycle machine. You're going to do likely hardwired control as a combinational function of instruction at memory PC. Right? Basically, you're going to examine what's in this memory location pointed to by PC, and based on that, generate the control signals. And you're going to be able, you're going to do this for ARM, but you're going to consider all of these instructions. The control logic should work for all of the instructions. For the MIPS design that we have, basically, the way to design the control logic, the easiest way to design the control logic, a single-cycle control logic, is go through all of the control signals that you have and decide when they're asserted and when they should not be asserted. and come up with an equation that actually satisfies that. For example, regdest. Regdest means which destination register ID to use. Remember, sometimes you write to RD, sometimes you write to RT, depending on the type of the instruction. Sometimes the register destination specifier comes from instruction bits 20 through 16, sometimes it comes from 15 through 11, depending on actually the opcode. R-type. R-type operations write to this. If opcode is equal to 0, actually, I did it wrong. R-type operations write to RD, because I-type operations don't have RT. You don't need to know this for an exam, by the way. I know this because I just know part of the MIPS ISA. If opcode is 0, then this is asserted. Otherwise, this is the assert. Make sense? And for some cases, you don't care, right? If opcode, there may be some opcodes that are not 0, but you're never going to write to a register. It's okay to deassert it, right? It doesn't matter in that case. This is just a simple function. Okay, ALU source. Remember, this is, again, does the ALU input, second ALU input, come from the second read port, or the second ALU input come from sign extended 16-bit immediate? Remember that? For those instructions that are R-type, let's see, opcode is not equal to 0. Yeah, that are I-type, so this is asserted when you want the immediate as your ALU input, second ALU input. If you remember this, let's go back. Yeah, there you go. Your ALU input can from this, can come from the register file or can come from sign extended immediate. When does it come from the sign extended immediate? Basically, it's asserted in that case. So you just need to figure out when that happens. When does that happen? If the instruction is I-type, basically opcode is not equal to 0, and if the instruction is not branch equal, and if the instruction is not branch not equal. These are the branch types that you need to consider. Yes?
Is there any guideline to deciding whether you're going to essentially go through the control signals and then case on the instruction, or vice versa? Like you go through each instruction and then define all the instruction signals for each.
You could do it either way, actually. You could do it either
Are
way.
there like benefits and drawbacks, or is it just it doesn't really matter?
I don't think it really matters. Whatever you're comfortable with. Maybe over time you find your personal benefits and drawbacks.
Mm-hmm.
But I don't. It's very hard to generalize.
Okay.
Okay. This is the way I think of it more easily, if you will. But if you can think of it more easily some other way, you could definitely do a table, right?
Mm-hmm.
Inputs and outputs, and you could actually give it to a solver and it gives you all of those equations. That's another way of doing it. You learn less probably by doing that, and you need to be able to set up the table and be able to verify it. But I like it this way because you really learn about the instructions. Okay, mem to reg. Remember, this is this mux that we added. You write the ALU result to the destination register, or you write the result data coming out of the memory to the destination register. And if remember the is load signal, only if the opcode is a load, then you write the you pick the data you want to write to the destination register from the memory. Okay, I'm not going to go through all of these basically. This is basically register write. Do you disable or enable the write to the register file? Basically all of those instructions that write to the register file, you go through all of them and you figure out which ones those are, and you enable the register write only for those instructions. Now this is the opposite. These are the instructions that do not write to the register file. Store, branch, jump register. Make sense? Okay, there's memory, memwrite, PC source 1, PC source 2. These are basically the control signals that determine what is the next PC, right? And these depend on which opcode, based on what we've discussed earlier. Okay, so ALU control, obviously you need to control the ALU also. These are the control for a lot of muxes. And this is easy in this case. You basically, you can do a case on opcode, right? If If it's 0, you can select the operation according to function, and function comes from actually the instruction itself. Remember that instruction format in MIPS, if opcode is 0, you have a sub-opcode called function that specifies what the ALU should do. And if it's an ALU, if the opcode is an ALU operation, you select the operation according to opcode. And if you're doing a load and store, you select addition because you need to calculate the address. If you're doing a branch, you select the branch condition generation function, right? Because you do different ALU operations depending on whether it's a branch equal, branch not equal, branch greater than, ... Well, otherwise you don't care probably what's happening in the ALU. Okay. That's simple. Okay, this looks like this died. So this could have told me also by saying something, right? This is fault-tolerant computing. Remember, some of the earliest fault-tolerant computers, a tandem computer, they used to design these important servers for banking and other applications. And they had something called lockstepping. And the idea was to have two processors that execute the same program exactly, and they check the output for every single instruction before committing the result. If the two processors agree on the result of the instruction, it's great. They assume that there's no faults that occur. If the processors disagree, then the tandem computer said, oh, there's a fault. And they actually lit up an LED in the box, a red bright light. And that was one of the most important features over there because that indicated to the operator that there's something wrong with this box here among all of the other boxes. So everybody, the operator would go looking for that red LED to replace the computers that are assumed to be faulty because the two processors disagreed. So indicating that there's a fault to the user is one of the most important parts of designing a good system. Yes?
What if there's a fault in the LED?
Yeah, that's your LEDs were more more robust at the time. But that's always a good question, fault-tolerant computing. You have this single point of failure, if you will, that you may not protect. But you can have two LEDs and check them also, right? You can incorporate all of those. You can incorporate redundancy at all levels.
Two operators.
Two operators too, that's right. Better eyes and all of those. Okay, let's take a look at how you switch these control signals. I'm going to go through this relatively quickly. But once you design the control logic, you should actually test the control logic operates nicely. For an R-type ALU instruction, muxes should be set up this way and control signals should be set up this way. I guess let's go through this. R-type ALU means that destination register ID comes from bits 15 through 11 of the instruction, so this mux should be connected this way. Make sense? And then register is going to be written because you're going to have you do write to the destination register. The second input of the ALU should come from the register output port, the second register output port, because it's a pure write to memory. And let's see, what is that mux? See, sometimes you need to think about that. Is it?
ALU output.
Oh, that's the ALU output. Yeah, you basically, you're right. You basically pick, this mux used to be here. See, that's the importance of consistency. Basically, whether you write to the destination register with the ALU output, which comes from here, or from the output that you come from memory, R-type instruction has nothing to do with memory, so you select the ALU output. Right? So you set up these muxes such that they work correctly. And also, here, this is a PC update logic. You need to select PC plus 4 somehow. So PC plus 4 is generated over here. It needs to be selected by this mux, and also needs to be selected by this mux, so you don't overwrite PC plus 4, and that gets circulated into the PC. Make sense? So here, PC mux plus here, this picture breaks it down over here. These are basically two muxes that control the input into the PC. You could have a one wide 4 input mux also. This just makes life a little bit easier. I-type ALU, basically, if you look at the difference, some control signals have changed, right? This is the I-type ALU. This is the destination register, and you select the immediate. Okay. Load word is a little bit different. You set up the muxes such that you ensure that you load from memory. The function is over here is add. You write to the register, and you still select PC plus 4. Store word is very similar. If you look at the difference, this is load word. Store word, basically, this is the memory write signal is asserted. Register write signal is this be asserted. And you really don't care what happens to these muxes, because you're not writing to the register, right? The stars don't care. Branch not taken. So this is a little bit different. Basically, this is a conditional branch. You're not writing to a register, so you don't care. Again, you're not writing to a register. Again, you don't care here. But you do care about the input to the ALU. The second input is really the register, output of the register file. And this is the branch condition that needs to specify the ALU result, ALU operation. And ALU output is fed to this mux over here. If it's a branch and branch condition is true, then you select this output, this input of the mux. In this case, I said branch not taken. This says branch. This is basically selecting PC plus 4 or the target of the branch. In this case, if it's not taken, if the branch condition says 0, this is going to be selected, and this should be selected. Make sense? So some control signals are dependent on the processing of data, right? Obviously, in this case. The control signal that controls this mux is really dependent on the branch condition. It's not all control signals will be generated here. Some of them will come from the processing in the data path. Okay? So you'll need to be careful. And this is true especially for branches, at least for the instructions that you're implementing. If the branch is taken, basically, the only difference is this mux needs to be set up such that this result, this ALU result, the branch target, is actually selected instead of PC plus 4. Okay? Again, some control signals are dependent on the processing of the data. This one. This mux control signal is dependent on that. Okay? Jump. Jump is actually very simple. You basically connect the jump target to the program counter. And everything else, do no harm. Jump is not going to write to the register, write to the memory, or read from memory. Right? Reading from memory can be harm also, right? In some way. Yes?
In the lab, are we also keeping the param counter separate from the other registers?
Yes, it's a good idea.
Okay. Makes sense.
Because architecturally it's separate from the other register. You could keep it in the register file, but that complicates a lot of things. In all processors, it's kept separate from the register file. Yes?
But aren't there like instructions where it's kind of the same? Like for example, if you did move PC OI, so you actually treat PC kind of the same as if it were a regular register in that case.
I see. So
there are cases where it's beneficial to treat it as any register.
yeah, but there are no such instructions as far as I know. Is there a move PC instruction?
Yeah.
Yeah, there's
Yeah.
PC OI.
That's
That's
the
how you
way you
return
return
from a
from
function.
function.
Oh, wait a second. This is a move instruction.
Yes.
Yes.
Okay. Well, you could translate it to jump, right?
Yeah.
It's the same as a jump, actually. It's just called a move.
Yes, but
Right.
but you would treat every move instruction the same except for that one, which would be a special case that now needs to be translated
That's right.
differently. So by having it outside of the register file, having the PC outside of the register file, you're making a special case for yourself
That's right.
in those situations.
But you have that special
So-
case anyway, right? For jump instructions, branch instructions. Because PC is not really addressable, right? Well, you could make it addressable. You could make anything. So
It
let
is.
me put it this way: you can implement anything anyway, actually.
Right.
Yes.
One problem is that the register file, you can only read two things and write one thing at once,
Mhm.
but even if you're writing another register, you're going to have to write to PC every cycle
That's right,
anyway.
yes. Well, you could increase the number of ports again to the register file. I don't know if we allow that. Rachada, do you remember? Can they change the register file?
I don't think so.
Yeah. Okay. Well, then there you go. But yeah.
Oh yeah, we also can't read PC here, right?
You can't read PC here.
Like as a value, because sometimes you just use PC for
That's
something.
right. That's right, yes. But you can translate one instruction to another instruction also. So for example, there are x86 processors that detect no-op instructions.
Would you recommend that against just having more data path logic, like just adding more muxes, translating it at the control level?
Sure, that's perfectly fine actually. Translating at the control level to a different instruction.
But it's
If you
not
can stick
necessarily
that.
better.
It's not necessarily better, that's right. It really depends on your critical path again. If your critical path doesn't go through that instruction, maybe translating is okay, right? And we'll do some critical path analysis, but you'll need to do it for yourself also. Okay. These are good questions though. There are a lot of implementation choices, even with a single cycle microarchitecture. Right? You could definitely add more and more things here. Right? Okay. So what's in that control box? This is what you're going to implement. You're going to have a combinational logic that's called the hardwired control. Basically, control signals are generated combinationally based on the instruction, at least for this control box. Some other control signals are generated based on the data processing too. This is necessary in a single cycle microarchitecture. What we'll later see, actually soon we'll see that you can have sequential logic that's implementing that control box, if you will. This is called sequential or microprogram control. And this is a nice way of designing machines. Basically, a memory structure contains the control signals associated with an instruction. You look up, based on the instructions, decode information, look up a control structure that gives you most of the control signals at least. Why most? Because some control signals need to come from the data processing rate. This is called the control store. And you're going to, well, if you do the extra credit assignment, you'll actually design a control store. Because in the extra credit assignment, we asked for a microprogrammed ARM microarchitecture. And I'd really encourage you to do the extra credit assignment if you're really interested in it and have time. If you do not have time, definitely do just the lab. Okay. Let's see what time it is. Maybe this is a good time to take a 5-minute break. Is that good? Let's come back at 1:33. Oh, sure.
Yeah, there'll be no way to return to a function, right?
Yeah, that's fine, I think. You're working with Diana? Yeah. Okay. When did you join? Exchange means swap. Make sense? So you could detect this at the decode logic and basically generate control signals such that this is a no-op. You could reduce the strength of this instruction. Why would you want to treat it as no-op? Well, you don't want to do this register movement, register swap, because it consumes energy. It may consume time also. And many x86 processors today that you use actually detect this instruction in the decoder and basically turn it into a no-op. Make sense? Why would anybody do something like this? Well, you may want to insert no-ops into your program, and we'll see reasons for that. Actually, because of this delayed branch, usually there are no-ops here. That might give you some good idea of why this exists. That's one reason to have exchange EX under a branch in MIPS, for example, although MIPS doesn't have exchange EX. Another example is if you can somehow do this, multiply by 0, right? If one of your operands are 0, either because of the immediate is 0, or because of a register value 0, if you can detect that as early as possible, you don't need to do the multiply. Right? If the immediate is 0, then, well, if the immediate is 1, also you could do special casing, right? Based on the data value of your operand that you could determine as early as possible in the pipeline, you can decide not to do some operations. If for example, if this is an immediate value, and if you decode it and compare it to 0, If you figure out that it's 0, then you simply turn this into a 0 operation into the destination register. Right? If the immediate is 1, and if you have special logic to detect it, then you simply turn this into, well, you're multiplying a register by 1. It's basically a move, right? If you have a register source, this is the second operand of the multiply. This is the first operand. And this is the register destination. If the immediate is 1, basically it's a move. Register destination, register RS, register source. You don't need to do the multiply. Make sense? So actually, the processors you're using do a lot of these tricks to optimize performance today. That's why some operations take variable latency. Yes?
Also, compilers often use XOR EAX to 0 a register because
that's true. Yeah,
it's a smaller instruction width. So
that's right. Exactly. That's another thing. That's another example.
In hardware too.
Yeah, you can have special hardware to detect whether the source and destination are the same. Then you turn it into just a 0, right? You don't need to do the XOR. Okay. Okay. Let's get back to evaluating the single-cycle microarchitecture. Well, I guess we've already answered a lot of these questions, right? Is this a good idea? Is this a good design? Single-cycle microarchitecture? Depends. I like the answer. It depends, actually. Maybe almost all the time it may not be a good idea, but there may be some cases it may be a good design. So it's always good to think about, think positively. There may be ideas that come along your way, and they may be very, very valuable in specialized cases. Right? So don't dismiss an idea because it may look terrible. Think about potential ways of actually places where it may make sense. And actually, the people who find those potential ways where it makes sense are the ones that enable those ideas to be successful. Well, single-cycle microarchitecture, most of the time it may not be a good idea because of the reasons that we discussed earlier. But when is this a good design? When is this a good idea? Yeah.
When you only have registers to operate on.
So that could be one place, yes. But there are other conditions probably. When all of your instructions take similar amount of time, right? Maybe actually that what you said, it helps that a little bit. But divide versus add still puts a lot of variability into latency.
Would it be useful in low power machines?
What machines?
Low power machines?
Low power. Maybe. I'm not sure. Because a lot of the power, this is actually a good discussion. It could be useful in the sense that you have maybe minimal logic. You don't have a lot of things. Although I'll debunk that a little bit later on. But it may take a long time, very long time to execute your program with this, because you may have a large clock cycle. As a result, your system may be operational for a long time, right? So you may be wasting a lot of power because your system is on for a long time.
But you draw the majority of your power in your clock edges, so if you have less clock edges over the time you're running, will you draw less power?
That's again an excellent point. Now you're making the distinction between dynamic and static power. Basically, dynamic power is consumed when you actually change the signals. This is on wires, right? At the clock edges, some signal changes. As a result, you need to dissipate some dynamic power. But there's also some static power that you consume regardless of whether or not you do any computation. Maybe nothing changes. Maybe you don't read out of the register file, but you're consuming power. Why?
Leakage.
Leakage. This is very similar to DRAM that we've discussed, right? DRAM capacitor leaks. Similarly, all those transistors actually leak because they're connected to some power source and they're also connected to ground, and there's some leakage that happens. And this is actually increasing in future technologies. So if your dynamic power is dominant, what you said perfectly makes sense. If your static power is dominant, then you may want to finish your program as soon as possible, perhaps consuming a lot of dynamic power. Right? So again, this is a trade-off. It depends is a good answer. But you need to also, of course, justify it depends. For example, when I ask you a question in the exam, just don't say just it depends. Tell me why it depends on and what it depends, what the answer depends on, right? Basically, if your static power is dominant, maybe you want to design a very, very fast machine that can execute the program and turn itself off very quickly. If your dynamic power is dominant, maybe you do it slowly, assuming performance is not a big concern. Okay, so this could be a good design when all of your instructions take the same amount of time, right? I don't know if there are such cases in real life, but depends again, right? Maybe you have a very limited set of ISA. Maybe very specialized part of your engine could be single cycle. Okay, well, I think we've covered this. When is a bad design? Well, exactly the opposite, right? How can we design a better microarchitecture? Well, I think we've talked about this also. So we're going to talk about multi-cycle microarchitectures. But remember, we've talked about the iron law of performance, right? And that was execution time of a program equals number of instructions in the program times average cycles taken to execute each instruction, cycles per instruction, times cycle time, clock cycle time. And this is in clock cycles, obviously. Okay? So in a single cycle machine, every instruction takes 1 cycle to execute. So cycles per instruction, this is strictly 1. Right? And how long each instruction takes is determined by how long the slowest instruction takes to execute. Even though many instructions do not need that long to execute, right? Which means that your clock cycle time can be very long. Clock cycle time of microarchitecture is determined by how long it takes to complete the slowest instruction. And, well, we already talked about this. Critical path of the design is determined by the processing time of that slowest instruction. As a result, this could be very long, right? And that's a problem. In fact, this may be hard to optimize. We'll get back to that again. So what is the slowest instruction to process? This begs that question, right? Let's go back to the basics. All 6 phases of the instruction processing cycle take a single machine clock cycle to complete. That's what we're going to assume for now. And I'm going to reduce this to 5 stages that I discussed earlier. Remember, there were 6 stages of instruction processing cycle. We're going to reduce that to 5. One question is, do each of the above phases take the same time latency for all instructions? Does instruction fetch take the same time? Probably yes, right? Because you're doing exactly the same thing. Instruction decode and register operand fetch, do they take the same time? Maybe not, right? Because some instructions do not need the register operands. But you're binding it to a clock cycle. Right? Execute evaluate memory address? Not really, right? Not all instructions do this. Jump instruction, for example, doesn't do it. Like I said, it evaluates the PC, so it does that. Memory operand fetch, again, not all instructions do this. Store write back result, not all instructions do this. Even when instructions do it, it could be different, right? In terms of real raw latency. Because execute may be just a simple XOR operation, or it could be a divide operation. Right? But let's assume that they take the same time right now. We're going to analyze which instruction takes the longest. I guess this is the analysis. I don't need to do more than this. But let's assume that the memory units read or write take 200 picoseconds, ALU and adders take 100 picoseconds, register file read or write takes 50 picoseconds, and other combinational logic is magic, 0 picoseconds. Wouldn't it be nice, right? I would implement everything in combinational logic, in other combinational logic somehow. So for R-type instructions, they do not need the memory stage of processing. So their delay is 400 picoseconds. Assume with these assumptions, assuming that all instructions take the same amount of time in these processing stages. I-type instructions, again, 400. Load, well, it turns out it needs all of the processing stages. It takes 600 picoseconds. Store, it doesn't need the write back into the register, 550. Branch, it doesn't need these 2, memory access and write back, 350. Jump is the simplest, right? Well, this is because we assumed other combinational logic takes 0 picoseconds, right? It's fake, but it gives you a ballpark, right? So this analysis shows that even within all of the assumptions that we've made, memory being magic, register file being magic, we still get variable latency in the instructions, right? 600 picoseconds for load, 200 picoseconds for jump. So maybe single cycle microarchitecture is not a great idea. And you can actually do this exercise. You could find the critical path. And I'm not going to go through this in detail. But if you do whatever we said previously, you'll see that R-type and I-type ALU instructions go through this critical path. This processing part is the critical path. It takes 400 picoseconds. There's also the PC plus 4, but that takes only 100 picoseconds. I think, yes. Load word, well, this is the longest. It takes 600 picoseconds. Store word, 550 because it doesn't write it to the register. Branch taken. Branch taken has actually two critical paths. One is the calculation of the target address, which goes through this ALU. And the second is calculation of the condition, which goes through this ALU. And this red one is longer, because there's more to do over here. You need to access the register file. And this is the jump, and dot, dot, dot. You can look at this on your own. This is pretty simple. What about control logic? How does that affect critical path? Actually, it is incorporated a little bit over here, except we assume that it's 0 picoseconds, right? So control logic does affect the critical path. I kind of ignored it in this analysis. And it's important to design the control logic such that it doesn't affect the critical path. We discussed this earlier, and we're going to harp on it soon. Basically, you're doing two kinds of processing in your data path in a single clock cycle. Generation of control signals and generation of data. And these are tightly coupled because control signals control how the data path elements treat the data. Right? And sometimes data signals enable the control of some muxes. Right? If the control logic takes too long, it can be on the critical path. And there were some machines actually where this is Control Data Corporation, old machines. We'll get to that when we talk about auto work execution. They had a control store. It wasn't hardwired control like we've discussed. But control store access was way too long. So they decided to break it down into multiple cycles. Okay. But single-cycle microarchitecture has this downside that we will again look into, that you have to generate the control signals at the same clock cycle as you're operating on data, which is a bad design. Okay. Well, there are other slowest instructions to process if you relax some of the assumptions we made, right? What if memory sometimes takes 100 milliseconds to access? Well, too bad. Now everything is out of the door. It's not 600 picoseconds, now 100 milliseconds. That's the worst case instruction. Terrible. And does it make sense to have a simple register-to-register add or jump to take 100 milliseconds plus all else to do a memory operation? Makes no sense, right? That's the downside of the single-cycle microarchitecture. And of course, if you need to do access memory more than once to process an instruction, you have another problem, right? You need to do 100 milliseconds plus some more processing, and that determines your clock cycle time. By the way, which instructions need more than one memory access?
In ARM, there's load, store, multiple.
Which one?
Load, store, multiple.
There's load, store, multiple in ARM. Yes, those are some instructions. What else?
Load byte.
Which one?
Load byte or store byte.
Okay, how so?
Actually, never mind. Sorry.
No, you're right, actually. Yes.
Any load store, because you need to load the instruction and then also perform the operation.
That's right, exactly. You'd get the question right on an exam. So remember, for every instruction, you're doing a memory access to load it, to get the instruction. Remember the mempc part? You take the program counter, access memory, and get the instruction. That's the first step, instruction fetch. And if you're doing load store, then you add one more memory access. That's it. And if the question was which instructions need to access memory, and the answer would be all instructions, right? Unless you have a special instruction that's sitting in the processor for some reason. Okay, anyway, we'll get to the multiple ports to memory later on. So basically, single-cycle microarchitecture is actually relatively complex in this sense. It's a little bit contrived because all instructions run as slow as the slowest instruction. It's inefficient because of that fact, which means that you need to provide worst-case combination of resources in parallel as required by any instruction. This requires some thinking, actually. Now, you cannot use the same ALU that you use to do add to also increment the PC, right? Because for the entire clock cycle, you've actually committed that ALU for some specific purpose. If you have single-cycle microarchitecture, you need to do 2 adds. You cannot do it with using the same ALU. But if you had actually broke down the instruction to stages and saved some results, you could actually use a single ALU to increment the PC in one cycle and to do the add in another cycle. Now you could get away with less hardware. You cannot do that in a single-cycle microarchitecture because you need to do all of those adds in a single cycle. So it's actually an inefficient design in terms of hardware cost. You could do much better. And this is a corollary of that. You need to replicate a resource if it's needed more than once by an instruction during different parts of the instruction processing cycle. I just gave you an example. So that's not necessarily the simplest way to implement an ISA. Well, if you have repeat moves, for example, index or polynomial evaluation, how do you do that? Repeat moves by definition require many, many accesses to memory. And it's also not easy to optimize and improve performance. One of the principles, design principles of microarchitecture, which we will discuss in the next slide, is common case design. The idea is figure out what's most commonly executed and optimize for that, because that's going to buy you most of the benefits in terms of performance or energy or reliability, whatever you're optimizing for. There's also Amdahl's law, right? You covered Amdahl's law. Basically, spend your resources on the thing that matters. Do you guys remember Amdahl's law from 2013? No? Okay, maybe I'll get to, I'll briefly discuss that. But the idea of Amdahl's law is you have, well, Amdahl came up with this equation when people were designing parallel processors. And parallel processors can speed up a program. But depends on the program. Program can have a serial portion. This is, let's call the serial fraction of the program that cannot be parallelized at all. And let's say this is the fraction, right? And 1 minus s is a parallel fraction. Assume that this is infinitely parallelizable. Basically, however many processors you put, you can reduce this. Let's actually change this. Let's call this p and 1 minus p. This is a parallel fraction of the program. This is a serial fraction of the program. Make sense? S equals 1 minus p, basically. Now, what is the maximum speed up you can get depending on the different values of p? As you add more cores, as you add more processors into the system. Well, I'll give you the speed up equation. Time it takes to execute, let's assume the time it takes to execute a program with one processor is equal to t. What is the time it takes to execute the same program with n processor? What do? Well, you have the parallel fraction and you have the serial fraction, remember? This is the serial time and this is the parallel time. Make sense? And the serial time you cannot do anything about. You can add a billion processors and this is not going to speed up because it's serial. The parallel part, it gets divided by n. Right? The parallel part gets reduced, divided by n. Because we assume that it's infinitely parallelizable. If n is infinity, this goes to 0. If n is 1, it's the same as this. Okay. So what's the speed up that you get with n processors? It's basically time it takes to execute the program with one processor divided by time it takes to execute the program with n processors. Which is, I'll get rid of t's. If you do this division, you'll see that you'll get 1 divided by 1 minus p plus p over n, right? You follow the math. And that's basically Amdahl's law, if you will. The speed up you get with n number of processors is really limited by what fraction of the program is serial or parallel. You could think of it both ways. As n goes to infinity, in other words, as n goes to infinity, this goes to 0, and your maximum speed up becomes 1 divided by 1 minus p. Right. Which means that, let's say you design a system with infinite number of processors. If your program is parallelizable only 50%, your speed up is 2, right? Kind of sucks. You designed 1 billion processors, and your speed up, the speed up you get over a single processor is just 2. Why? Because your serial fraction is your bottleneck. With those billion processors, that's not going to apply to this bottleneck over here. Your serial fraction is, in other words, the common case here, right? Even 50% is the common case in this case. On the other hand, if your serial fraction is, well, I guess 1 will give you undefined over here, so I'm not going to put 1. But if your parallel fraction is 0.999999, now you get huge benefits by adding more processors. Does that make sense? So that's the idea of Amdahl's law. It was developed for parallel processing, saying that the speed up you get with as you increase the number of processors is limited by the serial part of your program, but you could actually apply it to anything. The speed up you get from eliminating a performance bottleneck is dependent on how big of an effect that performance bottleneck had initially on the program's execution time. You could think of this as P as what fraction of the execution time was memory bound. Right? You're spending the time going to memory. And if you're optimizing for memory, let's say, if you improve memory performance by infinity, the only part of the program that's going to be affected would be the parts that are actually bound by memory, right? Those load store instructions that go to memory. And if that's not a significant part of your original execution time, then you're optimizing the wrong thing. Because you spend all this effort improving memory performance, you get very little benefit. 2x if memory performance is only 50% of your execution time. Right? Make sense? So that's the idea of common case design, and it's motivated. Well, Amdahl's law is a nice way of motivating it. It basically says spend time on the most important bottlenecks first, and then something else becomes a bottleneck, then spend time on it, and then something else becomes a bottleneck, then spend time on it. Okay? Okay. Basically, in this case, optimizing common case doesn't work though, because you may have common instructions, you may have lots of adds. You may be executing only adds in your machine. But in a single-cycle microarchitecture, how are you going to optimize that? Right? You're dominated by this huge divide that you're executing once in a blue moon. Right? Basically, you need to optimize the worst case all the time. This is not a good design. You need to optimize that worst case. And you're limited by how much you can optimize that worst case. Okay, so there are 3 design principles, one of which we've talked about. Bread and butter or common case design. But there are actually two other ones that single-cycle microarchitecture violates. Critical path design dictates that find the maximum combinational logic delay and decrease it to decrease the clock cycle time. Right? This improves frequency. Bread and butter we already talked about. Spend time and resources on where it matters. Improve what the machine is really designed to do. Improve the common case. And the third one is balance design. Balance instruction data flow through hardware components. Balance the hardware needed to accomplish the work. We'll get to this when we talk about pipelining especially. For example, if you're fetching, let's say 16 instructions per cycle, and if you have only one ALU, you can execute 1 instruction per cycle. That's not a balanced design, right? Why are you fetching 16 instructions per cycle if you can execute only 1 instruction per cycle? That's a bad design. Again, your memory can be the bottleneck. If you can do 10 loads per cycle, but you have only 1 memory port, that may not be a balanced design. Okay. So single-cycle microarchitecture actually fares really badly in light of all of these principles, especially these two. Let's see. Oh, we still have time. You guys wanted to go early? Yeah? Okay, let's see where we end up. I'd like to cover a little bit of multi-cycle microarchitectures. Well, you know what it is, right? Basically, the goal is to let each instruction to take close to only as much time it really needs. Well, close to because it's very difficult to give it exactly as much time it really needs. So the idea is determine the clock time independently of the instruction processing time. Each instruction takes as many clock cycles as it needs to take. You have multiple state transitions per instruction. And the states followed by each instruction is different. I think I've shown you this before. But basically, microarchitecture implements how the input architectural state is transformed to the output architectural state by an instruction. So we're going to do this. This was our choice 1, if you remember the slide. You take the input architectural state of an instruction, transform it to an output architectural state in a single clock cycle. We're going to use multiple clock cycles for this. Now we can optimize a clock cycle. Basically this. I'm going through this quickly because these are really simple concepts. Right? You can shout if actually something is not understandable. But benefits of multi-cycle design, now you can keep reducing the critical path independently of the worst case processing time of an instruction. Right? You've decoupled this. Because your critical path is independent of any instruction now. It's really dependent on whatever you define to be your clock cycle time. And you can keep reducing it. And you can optimize the number of states it takes to execute important instructions now that make up much of the execution time. Right? Instead of trying to optimize the worst possible instruction. And no need to provide more capability or resources than really needed. Right? Now you can have the same ALU, do PC plus 4 at one point, and do addition at another point. So you could design a very lean machine this way. Yeah, this is the same thing. So this leads to more efficient hardware. You can reuse hardware components that are needed multiple times for an instruction. So this performance analysis that we've done before, I'm going to go through this quickly. This is basically what I've shown over here. But basically now you have 2 degrees of freedom with a multi-cycle design. You can change the clock cycle time and make it really short and keep optimizing it. And you can also change the CPI because now it's different for each instruction. And you can hopefully make the average CPI small. So we talked about this very briefly last time, CPI versus clock cycle time. Clock cycle time is also frequency, right? Inverse of frequency. These are actually usually at odds with each other. If you reduce one, you increase the other for a single instruction. If you think about a single add, if you reduce the clock cycle time, you increase cycles per instruction. It's kind of obvious, right? Because at a raw latency, an add has some raw latency. It needs to do this work, right? It needs to be fetched, it needs to be decoded, it needs to access the register file, it needs to be do the ALU operation, it needs to write back the results. This takes some raw nanoseconds latency. I'll call it T-raw. Well, your clock cycle time determines how many cycles it takes, right? Basically, cycles per add is determined by T raw nanoseconds divided by T clock nanoseconds. And this equation simply shows that these are at odds with each other, right? As you increase T clock, cycles per instruction decreases. As you decrease T clock, cycles per instruction increases. Make sense? And this is actually a very fundamental principle, although we're going to try to overcome that a little bit. Well, I guess I've given you why. Could have been a good question. Okay. But average cycles per instruction can be amortized or reduced via concurrent processing of multiple instructions. One of you asked this after class. You can actually do multiple instructions in parallel. Now you're amortizing the same cycle over multiple instructions. That way you can actually go have a CPI that's less than 1. Or have multiple instructions per cycle. And you could do this through pipelining and superscalar execution. With pipelining, you cannot actually have a CPI less than 1, right? As long as you keep the pipeline full. At most, you're actually finishing one instruction per cycle. But superscalar execution, and we'll get to this, don't worry about this right now. Superscalar execution, you're actually fetching, decoding, executing multiple instructions per cycle, so your average CPI is lower, could be lower than 1. Okay. I guess maybe this is a good place to stop today, unless people want to really continue. I'll take a vote. Who wants to really continue? I guess some people are shy. Who wants to be done for today? Okay. I guess let's be done for today, and I'll see you Monday.
It's a lab check on things.
Oh, that's right. Yes, that's right.
It's a stressful day, yeah, you know.
What time is lab tonight?
6:30 to 9:30.